Good, ladies and gentlemen, thank you very much to the Director General, Martin de Maizière, to invite me here to try to show you how those last 50 years have been exciting times for aeronomy, but also for the science in general. And so, if and when the Aeronomy Institute was created in 1964, it came into an environment that was already very strong. The presence of the Royal Observatory, the presence of the Royal Meteorological Institute, with a number of people who had been creating an environment and have really provided scientific leadership at the international level. Jules Jomotte, for example, the director of the Royal Meteorological Institute between 1919 and 1940, had really introduced the modern method for dynamic and synoptic meteorology. A bit later, the director between 1962 and 70, Jacques van Mieghem, was really and still remain very much a leader in dynamic meteorology, but also introduced the first measurements of radioactivity and atmospheric chemistry, really at the basis of what the Aeronomy Institute took over as time was evolving. He recognized, for example, already that ozone needed to be measured on a regular way. Perhaps the third great personality at the time was Marcel Nicolais, who instituted in 1959 the National Center for Space Research, and then moved slowly but certainly into an institute that Minister Jeanne had proposed, or at least accepted, to create, the Belgian Institute for Space Aeronomy, very soon the Belgian Royal Institute for Space Aeronomy, looking at physics and chemistry of the Earth and other planets and even the outer space. As Martin de Maizière just indicated, aeronomy is the science of the atmosphere, but it's the science of the atmosphere that is a bit different from the meteorology. It is the science where the dissociation, the ionization of chemical compounds are important. And this is happening not only on Earth, but also on the planets. Well, if ionization, if dissociation are so important, we know that the source is really the sun. And so the Aeronomy Institute looked at the sun and started making, under the leadership of Paul Simon, looking in much detail of the spectral distribution of the solar flux, basically the forcing of our system, the natural forcing of our system. Moving then towards the Earth and recognizing that the solar corona was expanding and creating the so-called solar wind, a number of models of world class were developed by Joseph Lemaire and Marc Scherer in the beginning of the Institute and remain still very much as recognized today as a very unique way of understanding the relation of the sun and the upper atmosphere. Moving further towards the Earth, we have the thermosphere, the region of the atmosphere that extends above 100-kilometer altitude. And here, Gaston Coccatz and Marcel Nicolais were the first to develop really one-dimensional models that showed the distribution of chemical compounds more than 100 kilometers, thousands of kilometers high in the atmosphere, and the gradual change from nitrogen and oxygen into an atmosphere dominated by helium and by hydrogen. Now, this was the time of space research, the time where satellites were started to be launched, the study where the recognition of the work conducted in Uccle led, in fact, the Royal Meteorological Institute at that time, and Marcel Nicolais in particular, to be the host of the International Geophysical Year from 1957 and 58. Marcel Nicolais was the Secretary General, and you see here a meeting of the scientists in UCLE, deciding really about what the International Geophysical Year should be in the year ahead. Année Géophysicale Internationale, International Geophysical Year. You see that finally Nicolay was rewarded for all this work, here talking to the President of the United States, Lyndon Johnson. Well, as we move to the charge, to the electrically charged atmosphere, what we call the ionosphere, here also Belgium played a major role. And Nicolay in particular discovered, this was part of his, I think, thesis of aggregation, that the D region of the ionosphere is really created by the ionization of nitric oxide, which is present in the upper atmosphere. And you see here the thesis, the title of the thesis, but also the paper that was then published later on with Aiken, who had been working further on this problem. So NO+, ionized nitric oxide, was believed to be the dominant compound. But a few years later, it appeared that this was not really the case, that the chemistry was much more complicated, complemented by the formation of what we call proton hydrates in the D region with a complex chemistry that was identified in the United States. And that led a number of people at the Aeronomy Institute to look at this problem and at this question in much more detail, in particular to look how ions could be present in the lower part of the upper atmosphere, namely in the stratosphere, as a result of the action of galactic cosmic rays. And here we should remember the tremendous work that Etienne Arès has been conducting, showing that in fact below 60 kilometer altitude and in the stratosphere, the proton hydrates were replaced by non-proton hydrate through a reaction with a mysterious compound not identified at the time, which we called X, which had probably a high proton activity to link with the proton of this molecule. And in fact, those balloon experiments that were conducted from France, from Air Soladour in particular, identified this compound as being acetonitrile. We now say methyl nitrate, acetonitrile, CH3CN. And this compound was then, the concentration of this compound was deduced from those observations. In fact, this compound is coming essentially from biomass burning, from combustion, and is therefore a first fingerprint of humans into the ionosphere that was identified. Going back to the mesosphere, here also in this region between 50 and 90 kilometer altitude, Bates and Nicolay published their famous paper when they were looking at air glow, and I think Jean-Claude Gérard will probably say more about that, but identifying, in fact, that the hydrogen compounds coming from the water, evaporating from the ocean and moving up into the upper atmosphere were controlling the budget of atomic oxygen and ozone above 50 kilometer altitude. And you see here Bates and Nicolay. In fact, you see them again here during the sabbatical of both Nicolay and Bates, sitting with the great geophysicist Chapman at Pasadena, at Caltech in California. Let me now move to the stratosphere, the region between about 15 and 50 kilometer altitude. And here again, there's been much studies. Started at the Meteorological Institute by measuring ozone in a routine way and having a long record of data initiated, in fact, by Van Meeghem long time ago. But the problem really started when Paul Crutzen in 1970 showed that a way to destroy ozone, the major way, was not the one that Nicolay had identified for the mesosphere, but in the stratosphere, the reason of the destruction was the presence of nitric oxide, nitrogen oxide, which was probably produced by bacteria in soils through N2O. N2O diffusing up into the atmosphere was the source of nitric oxide. And so the question came up very rapidly. If we add nitrogen oxide, for example, by aviation, we could destroy ozone in an important way. Johnston at the University of California suggested that probably 50%, 60, 70% of the ozone could be destroyed in the future by a fleet of supersonic aircraft. And that triggered a major international program led by the United States, the gold age for stratospheric research. Of course, immediately the Belgian Institute for Space Aeronomy was called into these studies, and Marcel Nicolet wrote this landmark paper here, Stratospheric Ozone, an introduction to study. We were, I say we because I joined the Institute at that time, playing a major role. The role was not only theoretical, but also experimental, and Marcel Ackermann, for example, was pioneering observation here, in this case, methane, nitrogen dioxide. You see here other measurements of NO2 from infrared spectra that were recorded from the balloon, and in cooperation, by the way, with French colleagues, in particular André Girard, who had developed a spectrometer of extreme sensitivity. On the side of modeling, of course, a lot of work was made, and this is a paper that Nicolet and myself published in 1973, showing, in fact, that the nitrogen oxide present in the stratosphere was not coming, as believed in the past, from the upper atmosphere, from the thermosphere, but was really coming from below, and in fact, coming to a large extent of the natural processes from bacteria in soils. And you can see now that space observation can document all that, can measure all that, can monitor all these compounds. This is exactly the N2O, nitrous oxide, that Simon Chabrier has been analyzing here with part of the team of BISA. Now, in 1974, Stolarski and Cicerone highlighted in the US that not only nitrogen could destroy ozone, but also chlorine compound. And at that time, they believed that chlorine was coming essentially from volcanoes. But very soon after, Roland and Molina, you see them here in their laboratory, said, but there is an additional non-natural source, a source that is associated with industrial activity and domestic uses. And that's the production of the chlorofluorocarbons, the CFCs. By the way, the CFCs had been invented or discovered, used for the first time in Belgium. Not many people know that in the early 1900s, Swart built and developed the first CFCs that were then seen as the key compound for the destruction of ozone in the polar region, in particular for the formation of the ozone hole, which was reported for the first time around 1984 and triggered another study of the stratosphere. You see here the depletion of ozone recorded at the Halley Base Station by the British group and Farman and co-workers without explanation, but all that had happened in 10 years, and so triggered a lot of anxiety and also the need to understand what happened. In fact, the Americans had not reported any ozone hole until they went back to their measurements and started to realize that, yes, indeed, if you look at our data, they said, you see the beginning of a big depletion over Antarctica. These are observations reported in 1985 after the British had really pulled the trigger and said, be careful, something is happening there. Now, since then, of course, we have observation from space. You see in the middle the ozone hole, and the ozone hole confined during August, September, and October in the polar vortex. You see that it happens in regions where the temperature is very low and where chlorine monoxide on the left there is very high, is elevated, and the mechanism, of course, were considered, discussed, and finally discovered. We now understand very much what's happening, and we know, of course, that it's a human-induced problem, and for that, Paul Crutzen, Mario Molina, and Sherry Rowland shared the Nobel Prize in Chemistry in 1995. By the way, Nicolet was mentioned in the citation of this Nobel Prize as being a major contributor to the science. Since then, of course, we continue to monitor ozone, CFCs, and all the other compounds. And BIRA, of course, is contributing very actively to this monitoring, with the hope, of course, that we see a decline, a gradual decline in the CFCs and other halocarbons. And we monitor, and they monitor ozone. You see here, for example, an observation from space showing that at times you can have very large destruction of ozone, not only in the Antarctic, but also in the Arctic region. And we're not that far away because Northern Europe can be affected sometimes, like here in 2011, by very, very strong ozone depletion that are happening in an area where the temperature is very low, and the mechanisms that exist in Antarctica happen also in the north. A few words about the lower atmosphere, the troposphere. And here, of course, I would say we have to deal with tropospheric ozone. Tropospheric ozone is a pollutant, and we see that it has a very complex distribution with maxima in the subtropical jet stream. High value over the Atlantic, but at the same time, low value over the Pacific. One's associated with lightning, the other one with convection. Also affected by El Nino. So a very complicated problem, and of course, observation of compounds that are at the source of ozone production, like carbon monoxide here, for example, are very important. You see here other compounds like gloxial, which are more the source of aerosol and produced to a large extent by biogenic activity and fires. You see that finally the satellite have provided a unique picture of a number of Earth system problem and questions that are occurring. And today, of course, we have models. This is the NCAR model that I've been involved, but with the help of Jean-François Muller and BIRA here, where we can really simulate in great detail what is happening in terms of the atmospheric composition of the troposphere, with resolution here of 50 kilometer altitude. How much time do I have? Sufficient. Okay. Then I will say that all this research has a societal relevance and can be used for operational application. Satellite, model, ground-based observation are the source of assimilated data that are then used to drive models and make the models as realistic as possible to produce consistent field of the chemical composition of the atmosphere near the surface. And BIRA contribute to a European project called MAC, Monitoring Atmospheric Composition and Climate, where a number of products, air quality forecast, stratospheric ozone record, UV index, aerosol forecast, methane emissions, greenhouse gas emissions, are produced on an operational and regular way. This was the prediction for a few days ago that I picked while I was preparing my talk, showing you, for example, carbon monoxide as predicted for the 21st of November 2004. You see immediately the high value over Asia and China in particular. You see the value in Africa associated with the biomass burning, or South America, the pollution also, and some fires probably in Canada. The nitrogen oxide are equally well predicted, where you see the distribution as predicted for that particular day. Again, high value over China. You even see the tracks of the ships over the ocean, which are one of the major sources in the Southern Hemisphere. Now, all these data, and this is now another compound, this is formaldehyde, can be used, and this was done at the Aeronomy Institute, by basically combining observations and models to look at or to deduce what are the optimized emissions and the emissions of the precursors of formaldehyde, in this case isoprene, which is produced essentially by the biosphere. So you can use these models to constrain a number of processes that occur, and this is another example here where you see observation of formic acid, and you deduce from there essentially what the emissions of formic acids can be and what the deposition, and therefore, because it's an acid, the acidity of the precipitation, acid rain can be. And you see that in particular, in the boreal region, in fact, a lot of the pH, or the acidity, is associated with the oxidation of some hydrocarbons, volatile organic compounds, coming from the trees, from the conifers. Finally, BIRA had had great moment of pride. And I think one of them is when my friend Dirk Frimout, who is here on the first row, became an astronaut. And I couldn't resist, we know each other for more than 40 years, I couldn't resist to show a few pictures of him. You can see that, of course, it's different to be an astronaut or to talk to the king. You have a different suit on you, but at least it's been a wonderful journey. And of course, a big pride for the Aeronomy Institute, since Dirk was a scientist. We were a neighbor at that time. So what I would like to do is to conclude by first congratulating the Aeronomy Institute and in particular the Director General. I would like also to say that over the last 50 years, Belgium and in particular the Aeronomy Institute have played a key role in support of the international research of atmospheric sciences. It's recognized worldwide. The success must be attributed in large part to the support provided to a number of world-class scientists, in particular by BELSPO, by the European Commission and other national and international organizations. I highlight BELSPO here for a minute because I know, and the president of BELSPO is here, that there are some ideas or projects to change considerably the organization. Well, everything can be changed, but it remains very important, I believe, that we keep in Belgium a strong way of supporting science. The Aeronomy Institute would not be successful if there hadn't been a ministry that has changed name perhaps over the time, but a support that is coming from the government. And if this disappears, of course, this will be dramatic for the science, not only in Belgium, but at the international level. I'm saying that from being a bit outside now. The other point that I would like to say is that a world-class reputation requires a clear and long-term commitment to research, including fundamental aspects. Unfortunately, the trend in current fundings does not sufficiently recognize, this is everywhere in the world, the importance of fundamental research and fundamental activities. So remember that, and again, happy birthday to BIRA.